Welcome to a sim code. Hey, you. Want to join me in the world of coding? I promise it'll be more fun than you think. Hit that subscribe button and let's create some tech magic together. A stack in C is a linear data structure that follows the last in, first out, LIFO, principle, meaning the last element added is the first one to be removed. Think of it as a stack of plates. The plate you put on top is the first one you'll take off. In C, a stack is typically implemented using an array, with an integer variable called top to keep track of the last inserted element's index. The stack supports several basic operations: push, which adds an element to the top; pop, which removes the top element; peek, which allows you to view the top element without removing it; and is empty and is full, which check whether the stack is empty or full, respectively. In a stack, overflow occurs when you try to push an element onto a full stack, and underflow happens when you try to pop an element from an empty stack. Stacks are widely used in situations such as function call management, call stack, expression evaluation, and backtracking algorithms like maze solvers. By implementing a stack in C, you learn how to manage data in a controlled way, following specific rules to ensure efficient and error-free operations. Include standard input-output library for using printf to display output. Standard library for general utilities, though not directly used here, it's often useful in dynamic memory allocation. Define a constant max to represent the maximum capacity of the stack. Max determines the maximum number of elements the stack can hold. If you want to change the stack size, just modify this constant. A stack is a linear data structure that follows the LIFO, last in, first out, principle. The LIFO principle means that the last element added to the stack is the first one to be removed. It supports two basic operations. 1. Push adds an element to the top of the stack. 2. Pop removes the top element from the stack. Additionally, you can check if the stack is empty or full, or peek at the top element without removing it. Array to store the elements of the stack. This array will hold the values pushed onto the stack. The maximum number of elements is defined by max, 5 in this case. Top variable keeps track of the current position of the stack, for example, the index of the last inserted element. It helps determine where the last pushed element is located and controls the operations of push and pop. Function to initialize the stack. This is the first thing that happens when you create a stack object. Set the top to -1 to indicate the stack is empty, no elements yet. -1 is used because array indexing starts at 0. By initializing it to -1, we signify that no element has been pushed yet. Print confirmation that the stack has been initialized. Function to check if the stack is full. This helps prevent stack overflow. If the top is equal to max minus 1, it means the array is fully occupied. The last valid index in the array is max minus 1, so if top reaches this value, the stack is full. Return 1, true, indicating the stack is full. Return 0, false, meaning the stack is not full and there is space for more elements. Function to check if the stack is empty. This helps prevent stack underflow. If the top is minus 1, it means there are no elements in the stack. If top is minus 1, the stack is empty because no elements have been pushed yet. Return 1, true, indicating the stack is empty. Return 0, false, meaning there are elements in the stack. Push function to add elements to the top of the stack. Check if the stack is full before attempting to push an element. If the stack is full, print an error message and stop the operation. Overflow error. If you try to push an element into a full stack, it leads to stack overflow. It is crucial to prevent this condition by checking if the stack is full before pushing. If the stack is not full, increment the top and store the new element at that position. Increment the top by 1, then store the value at the new top position in the array. The top points to the index where the next element should be inserted. Print a message confirming that the element was successfully pushed onto the stack. Pop function to remove the top element from the stack. Check if the stack is empty before attempting to pop an element. If the stack is empty, print an error message and stop the operation. Underflow error. If you try to pop an element from an empty stack, it leads to stack underflow. We need to check if the stack is empty before popping to avoid this condition. Return -1 as an error code to indicate the pop operation failed. If the stack is not empty, return the value at the top of the stack, then decrement top to remove it. Save the value at the top, then decrement the top by 1. This effectively removes the element from the stack by moving the top pointer down. Print a message confirming the popped element. Return the value that was popped from the stack. Peek function to view the top element of the stack without removing it. If the stack is empty, there is no top element to peek at. Print an error message for empty stack. Return -1 as an error code to signal that the peek operation failed. Return the element at the top without removing it from the stack. The top element is the last element inserted in the stack. The main function that drives the stack operations. Declare a stack variable called myStack of type struct stack. Initialize the stack using the initStack function. Pass the address of myStack. Demonstrating push operation with different values. Push the value 10 onto the stack. Push the value 20 onto the stack. Push the value 30 onto the stack. Push the value 40 onto the stack. Push the value 50 onto the stack. Attempting to push one more element when the stack is already full. Trying to push 60 onto the stack, but the stack is already full. Max size is 5. This will trigger an overflow error since the stack cannot hold more than 5 elements. Demonstrating the peak operation. We want to view the top element without popping it. If peak was successful, stack was not empty. Print the top element of the stack. Demonstrating the pop operation. We will remove elements from the stack. Pop the top element from the stack. This will remove the element 50. Pop the next element. This will remove 40. Pop the next element. This will remove 30. Continue popping until the stack is empty. Pop 20 from the stack. Pop 10 from the stack. Trying to pop from an empty stack, which will cause stack underflow. The stack is now empty, so this operation will trigger underflow. This error is caught by this empty check before attempting to pop. End the program. In summary, a stack is a simple yet powerful data structure that follows the LIFO principle. It is useful in a wide variety of applications such as expression evaluation, function call management, and undo operations. By understanding and implementing a stack in C, you gain a deeper understanding of how data structures and algorithms work at a low level. Now run our code. I hope you had fun. Don't forget to like and hit the subscribe button.